So this problem is about a linear system with the possibility of drawing the graphs or sketching the graphs of the solutions in the phase plane. So this is something we did not do before. So let's tackle this problem then. So we have the system is dx dt equal minus x minus y dy dt equal minus 4x plus 2y. So first the coefficient matrix. We need the coefficient matrix. A equal minus 1, minus 1, minus 4, 2. Next we get to the characteristic equation. So it's lambda squared minus the trace. So we have to add the element on the diagonal. So we get minus 1 plus 2 lambda plus the determinant, which is minus 2 minus 4 times minus 1, that's plus 4, equals 0. This is very important to be careful and make sure that one has the right characteristic equation, otherwise the wrong eigenvalues and therefore the wrong solution. So this minus 1 plus is going to be plus lambda. Sorry, it's minus lambda. So it's minus plus 1, so it's minus lambda. Minus 2 minus 4 equals 0, so it's lambda squared minus lambda minus 6 equals 0. And this is easy to see that this is lambda minus 3 times lambda plus 2 equals 0. So the roots are, okay, so the two eigenvalues are minus 2 and 3. So next we need to find the eigenvectors. x1, y1 for each lambda. So first, lambda equals 3, we get, so the system that will give it to me is minus 1 minus 3 x1 minus y1 equals 0, minus 4 x1 plus d2 minus 3 y1 equals 0. And it's very easy to see that the two equations reduces to the same equation, okay, which means y1 equals minus 4x1. So the vector x1 y1 is x1 minus 4x1, which means like minus 4. So this will give me all the eigenvectors associated to lambda equal 3. And now we go to lambda equal minus 2. So the system in this case is minus 1 plus 2, because this is minus lambda, x1, b, y1, and then c, x1, plus d minus lambda y1 equals 0, which gives us minus x1 minus y1 equals 0 and minus 4x1. So the first equation is x1 minus y1 equals 0. The second equation is minus 4x1 plus 4y1. In other words, the second equation is minus 4 times the first one. So the two equations are the same, which means y1 equals x1. So the vector, the eigenvector is x1, x1, x1 times 1, 1. So the two solutions, the general solution now, the general solution is C1 times E 3T1 minus 4 plus C2 E minus 2T 1, 1. So this will give me all the solutions. So next, we want to find the solutions in the phase plane. So we want to phase plane. So we want to draw all, to sketch the graph of all the solutions. So here we have y-axis, x-axis. So I need to draw the constant solutions. So the straight line solutions will be, so I have to find, so the first one is the lambda equals 3, and for that we have 1 and minus 4, the vector. So this is 1, 2, 3, minus 4. So this is the point. So this is for lambda equals 3. And for lambda equals 1, lambda equal negative 2, we have 1, 1. So it's 1, 1. So this is the straight line that corresponds to lambda equal negative 2. So we know now that the solutions, first you have the equilibrium point solution, and we know it is a saddle because one eigenvalue is positive, one eigenvalue is negative. Along the negative eigenvalue we go and die at the equilibrium point, while along the positive eigenvalue, behave like a source, we are going away. Okay? So the other ones, they will be coming from the negative one, and they will be going to the positive eigenvalue. Sorry. So basically the solutions are like this. And finally, we are looking at the solution that satisfies the initial condition 1, 3. This is 1. So this is the initial point. So we know that the solution will be coming from go to the initial point and go to the other one.